In this video, we are going to introduce the starting concepts of linear algebra. For that, we're going to start by looking at some things that we already know. So we're going to start with some systems of linear equations. So when we're talking about systems of linear equations, the place where you usually start with this is we start by looking at equations like y equal 1/2 x plus 1/2. And we know this is a linear equation because we know the equation of a line is can be written in the form y equals mx plus b. And so in our equation, we have the m is 1/2 and the b is 1/2. So y equals 1/2 x plus 1/2 is the equation of a line. That's not how we will usually want to write this in linear algebra. Usually we would write this, we would move all the variables to one side. So we subtract 1/2 x from both sides. To get that. And this looks nice. It's got all the variables on one side and an answer on the other. But I don't like that negative 1/2. It's just a preference. This is fine. But I would prefer to not deal with that negative 1/2 in front of the x. So I'm going to multiply this entire equation by -2. So I'm multiplying by -2. And when I do that, I get that x minus 2y is equal to -1. And this is the form that we are usually going to want to think of in terms of our equations in linear algebra. In fact, we're going to step away from even using x and y eventually and replace it with just x1 minus 2x2 is equal to -1. And that way we won't be limited to just x and y. But for the moment, we'll stay with x and y. And I want to look at what this equation looks like when I plot this as a graph. So I can go to Desmos, and I can plot x minus 2y equal -1, and I get this line. Now, that line is not a system of equations. That's just a single equation. If we are talking about a system of equations, then we are going to be talking about having two different ones of these equations. So a system, or at least two, in this case we'll start with 2. So a system might be something like x minus 2y is equal to -1, and -x plus 3y is equal to 3. Now I've got two different equations that together form the system of equations. And I can graph both of these. So if I jump back onto Desmos, if I graph both of them, I get the x minus 2y in red, the x minus 2y equals -1 in red, and the x plus 3y equals 3 in blue. And if I look at where they intersect, they intersect at this point 3, 2. And so my solution would be x equal 3, y equal 2. So we can get a solution just by looking at where these lines intersect. But what if our system looks a little different? What if instead of that I have a system that looks like x minus 2y equal -1 and -x plus 2y equal 3? Now, if I go back and I graph that, I'm going to get these two lines. And these two lines are parallel. So they are never going to intersect, so there is no solution to this system of equations. I could also have a system of equations that looked like x minus 2y equal negative 1 and negative x plus 2y is equal to 1. And if I graph these, well, the two equations are graphed exactly on top of each other. So in other words, these are parallel lines, but they're actually the same line. And so every point on this line is on both of those lines. Every point on this line is a solution to the system of equations. So that's our starting thought process. So if we're working with this, we don't usually want to actually make these graphs because these graphs are a lot of work and it can be imprecise where to find the solution. So what we will usually want to do is work with solving the system of equations simultaneously and work with solving processes. You've seen this in like your college algebra class or one of those types of things. So I want to we're going to concentrate just on this first system of equations. I'm going to rewrite this not with x and y, but with x1 and x2 because it's just more general. So I'm going to rewrite this system as x1 minus 2x2 is equal to negative 1, and negative x1 plus 3x2 is equal to 3. And just because I want to be careful, I'm going to make sure that that is clearly a 1. Now this is the exact same system of equations. I've just replaced x with x1 and y with x2. So I've just renamed them. Now I can rewrite this exact same information. I can be a little bit more efficient in how I write it. And mathematicians, well, we're lazy, so we want the efficient way. We don't want to put in too much effort to write these equations. So we write these equations, represent equations in something called a matrix. And so if we think about a matrix notation for this, there's two different matrices. Matrices is the plural of matrix. There's two different matrices we could use. The first one is called the coefficient matrix. And the coefficient matrix, you form that by making a little box. And then I'm going to represent two columns, the x1 column and the x2 column. And then I'm just going to write down the coefficients. So the first equation said x1 minus 2x2. Well, the coefficients are 1 on x1 and negative 2 on x2, because I can think of that as x1 plus a negative 2 times x2. And on the second equation, I've got a negative 1 and a 3. And this is the coefficient matrix. I've represented all the coefficients from my x's, from my variables, in this matrix form, and I can keep track of what it is. We usually don't bother write the x1 and x2, but it is, you can think of it as each column represents the coefficients multiplied by x1 and multiplied by x2. There is obviously something missing though, and the thing that's missing is I don't know what these are equal to. So we fix that by making what we call the augmented matrix. And the augmented matrix, augmented just means we're adding something to it. We're augmenting it, we're adding on. And so the augmented matrix is going to be the exact same thing, except we're going to have our x1 and x2, which we don't usually write, but I am going to for the moment. And then we're going to put the thing that it's equal to. We're just going to augment it with what it's equal to. And so the first equation becomes 1 times x1 plus a negative 2 times x2 is equal to negative 1. The second equation becomes negative 1 times x1 plus 3 times x2 is equal to 3. And so now we have the augmented matrix. It's got all of the information in it. And We can use this augmented matrix to solve the system of equations. At this point, it feels kind of useless because we've got methods to do this pretty quickly when it's a 2x2, but this is going to generalize into a more useful tool as our matrices get bigger. So let's rewrite this. The matrix that we're solving, the system of equations that we're solving is x1 minus 2x2 is equal to -1, and negative x1 plus 3x2 is equal to 3. And just so we can keep track of what we're doing, I'm going to also write the augmented matrix, and we're going to solve both of these simultaneously. And in our augmented matrix, remember this first column represents x1, the second column represents x2, and the third column represents the thing that it is equal to. So if we're solving our system of equations, we're going to use the elimination method that you learned in college algebra. So I'm going to add equation 1 to equation 2. And the equivalent thing to do in the matrix is add row 1 to row 2. So when I add these together, I'm adding equation 1 to equation 2, so equation 1 stays the same. So I'm just going to copy that down. And then when I write down equation 2, I'm going to add equation 1 to it. So I've got negative x1, but I'm adding x1. So that gives me 0x1. I've got 3x2, but I'm adding negative 2x2. So 3x2 plus a negative 2x2 is just plus x2 is equal to 3 plus a negative 1 gives me 2. Or in the matrix, my first row stays the same. And I add that to the second row. So negative 1 plus 1 is 0. 3 plus negative 2 is 1. 3 plus negative 1 is 2. Now I'm going to just multiply row 2 by 2 and add it to row 1. So the way I can say that is I can say I'm going to add 2 times the second equation to the first equation. Or in the matrix, that would be adding 2 times row 2 to row 1. So when I do that, my second equation is going to stay the same. And when I write down the first equation, I'm taking x1 plus 0x1 is just x1. Negative 2x2 plus x2 is minus x2. I'm sorry, I did that. I've got to be more careful. So the x1 plus 0 times 2 x1 is x1 plus 0 x1 is x1. Negative 2 plus 2 times x2 is plus 0 x2. And negative 1 plus 2 times 2 is negative 1 plus 4 is 3. Or in my matrix, that would be the second row stays the same. And in the first row, I take 1 plus 2 times 0 is 1. Negative 2 plus 2 times 1 is 0. Negative 1 plus 2 times 2 is negative 1 plus 4 is 3. And now from my equations, I can read, well, a solution would look like x1 is equal to 3 and x2 is equal to 2, which was that 0.3, 2 we found in the graph. But remember, my rows represent x1 and x2. And so I can read from row 1, I'm getting 1 times x1, or just x1, plus 0 times x2, I can leave that alone, is equal to 3. And 0x1, that's nothing, plus 1 times x2 gives me x2 is equal to 2. So I can read that off of the matrix as well and not have to keep rewriting these equations again and again. And this process is going to allow us to shortcut a lot of the elimination method by not having to rewrite the entire equation, but just keep track of the numbers involved. So this works because whenever I add the same thing to the left side and the right side of an equation, I get an equivalent equation. And so as long as I'm never changing my equations, I'm getting an equivalent system of equations. And so we say that each one of these modifications I made gave me an equivalent system. And so we'll say that the matrices are equivalent with each of those modifications. So what's important for us to know is what modifications can we make. And so the modifications we can make to a matrix. So these are modifications we can make to a matrix to get an equivalent matrix. And mathematicians have given these a name. These are called the elementary row operations. The first one, some people call this the replacement. And this is the only one that we used in my example. But the replacement says we can replace one row by itself plus a multiple of another row. And so the first thing we did was we replaced row 2 by itself plus 1 times the first row. The second thing we did was we replaced row 1 by itself plus negative 2 times the second row, or maybe it was 2 times, I don't remember, by 2 times the second row. So that's what we can do. That's one of the things we can do. The next one, this is sometimes referred to as interchange. And what interchange kind of means flipping or flopping or switching or something along those lines. And so the interchange operation is you can interchange or flip two rows. This might not be quite as obvious because it's not something that we really talk about in like a college algebra class. But the thing that you can think about is if I'm writing down equations, the order I write the equations down doesn't change the system. And so flipping two rows, like switching row 1 and row 3, or row 1 and row 2, just writing them in the opposite order, is the same as changing what order you wrote down the equations in the system of equations. So that's not going to change anything. The third one that we can do, and this is called scaling. And what scaling is you can multiply all entries in a row by a non-zero constant. So what do we mean by a constant? Well, a constant is just a mathematical way of saying by a number that doesn't have a variable involved. It's just a number. And so these, if you can take a augmented matrix and you do these row operations, any of them that you want to do, you will get an equivalent matrix, and if you converted it back to a system of equations, it would have the same set of answers. So you can do these as many times as you want in any way that you want, as long as you don't make any mistakes in doing your calculations. You won't be changing your answers. You'll get the same answers out. So in linear algebra, we frequently want to answer two questions about a system of equations. So there's two big questions. The first one is the system consistent? And that's a word that we don't normally use in this way, so let's restate this in a way that that actually makes more sense with if you don't know the word consistent in this setting. And so another way to say this is, does at least one solution exist? And the second question is, if a solution exists, is it unique? And what we mean by that is it the only one? Or are there more than one solution? And so to see this, I want to illustrate this point using a little bit of a more involved example. So I want to start with a set of equations. And the set of equations I'm going to start with is going to be, and I'm going to write this to the right because I want you to be able to see it when I show you the picture, the image. But I want to start with the set of equations 0x1 plus 0x2 plus x3 is equal to -2. X1 plus x2 minus x3 is equal to 0. And 2x1 plus 2x2 minus x3 is equal to 0. And I'm going to show you these graphed in red, blue, and green. And so when I show you this graph, it looks like this. This is the graph. I can turn it and we can see what it looks like from different angles. And notice, now since we're dealing with 3 equations, when I graph this, the system, the software I've got to graph it, requires me to write it in terms of x, y, and z and solve for z. So these equations don't look the same, but they are the same. And what I get is each line in 3 dimensions represents a plane. So instead of a linear equation giving us a line, these linear equations, these 3 linear equations, each give us a plane. And if I look at where these planes intersect, well, there are places where any 2 of them intersect, but all 3 of them together never ever intersect. There's this little triangular gap that the 3 of them never ever intersect, which means there is no point anywhere on here that is on all 3 of these planes, which means there is no solution. Or written another way, we could say this is not consistent. But I could take this same basic graph and rewrite it as the same basic equation system of equations, but I'm going to slightly modify it. 0x1 plus 0x2 plus x3, and instead of saying it's equal to negative 2, I'm going to say it's equal to 0. And the other two I'm going to leave alone. And what that's going to do, I'm going to graph that in red, blue, and green again. And what that's going to do is, because I've moved that first equation, the red plane, I've moved it up by 2. Instead of saying x3 is equal to negative 2, I'm saying x3 is equal to 0. I've moved it up by 2. What that's going to do is I'm no longer going to have the z equal to negative 2. I'm now going to have z equals 0, this plane. And if I look at this, there is a line, this line, where all 3 planes intersect along that line. So I took, and I can just rotate any one of these planes to get the other planes if I rotate along this line. So that gives me infinitely many solutions. So this is consistent, and there are infinitely many solutions. We can take and we can make another system of equations. This time I'm going to be a little bit more interesting. Let's look at x1 plus x2 minus x3 equals 0. That's going to get plotted in red. x1 minus x2 minus x3 is equal to 0. That one we will do in blue. And 0x1 plus 0x2 plus x3 we will do is equal to 3. We will plot in green. And so when I do that, I'm looking at this set of planes. And this set of planes, it looks like, well, there isn't a single line that all 3 of them connect at. Instead, there's this point. The 3 planes intersect exactly at this point right here. And so no matter which plane I'm looking at, let's go a little slower than that. No matter which plane I'm looking at, that point is on all 3 of those planes. And so that means it's consistent. There is a solution. And there's exactly one solution because there's only that one point where all 3 planes intersect. So this is a consistent solution. I want to look at each of these situations and see what happens when we work with them, not graphically, but by working with them directly on the paper. How can we calculate with these? So let's start with that last equation, the one that had one solution. Excuse me. This is probably the one that most of us think of and is the most common one that you will see as a problem in a textbook in a class like this, but certainly not the only one type that you will see. So this is the equation, x1 plus x2 minus x3 equals 0. x1 minus x2 minus x3 is equal to 0. And 0x1 plus 0x2 plus x3 is equal to 3. Just a note, a lot of times when you're writing the equations, you won't bother to write the variables that are multiplied by 0. So you would frequently see it written like this. I want to work with this not in the system of equations, but rather as an augmented matrix. So my first column is going to represent x1, then x2, then x3, and then the equal, what it's equal to. So then my first row would be 1, 1, negative 1, 0. My second row would be 1, negative 1 because I've got 1 times x1 plus negative 1 times x2, negative 1 because I'm doing plus a negative 1 times x3, and then 0. And the last one is 0, 0, 1, 3. So I'm going to do row operations. And these elementary row operations, the first thing I'm going to do is I'm going to add row 3 to row 1. When I do that, I get 1, 1, 0, 0. And then the other two rows stay the same. Then I'm going to add row 3 to row 2. The first row is untouched. The second row becomes 1, negative 1, 0, 3. And I'm sorry, I made a mistake because when I added row 3 to row 1, I should have gotten a 3 there. And the last row stays the same. Now I'm going to add row 2 to row 1. When I do that, I get in row 1, I get 1 plus 1 is 2, negative 1 plus 1 is 0, 0, 3 plus 3 is 6. Then I'm going to scale row 1 by 1/2, meaning I'm going to multiply row 1 by 1/2. So 2 times 1/2 is 1, and 6 times 1/2 is 3. Then let's scale row 2 by negative 1. That's going to give me 1, 0, 0, 3 for the first row, untouched. The second row, I'm scaling by negative 1, so I'm multiplying everything by negative 1 to get me negative 1, 1, 0, negative 3. And the third row stays untouched. Now I'm going to add row 1 to row 2. When I do that, I get 1, 0, 0, 3. When I add row 1 to row 2, I get negative 1 plus 1 is 0. 1 plus 0 is 1, 0. Negative 3 plus 3 is 0. And so remember, the first column represents x1. So I get from the first row that x1 is equal to 3. From the second row, x2 is equal to 0. And from the third row, x3 is equal to 3. Which means the point that I am, all three of these intersect at is 3, 0, 3. And so when you get to something like this, where you can get exactly what each number is, that gives us the single point of intersection. But what about when that doesn't work? So I'm going to rewrite the first version. That was x3 equal negative 2. x1 plus x2 minus x3 is equal to 0. 2x1 plus 2x2 minus x3 is equal to 0. And this was the one that didn't have any solutions. So let's see what happens when we try to solve this system of equations when there are no solutions. The first thing we do is we write this as in matrix notation. So I'm going to write 0, 0, 1, negative 2, 1, 1, negative 1, 0, 2, 2, negative 1, 0. And the thing I want to do first of all is I want to interchange row 1 and row 3. Now I don't have to do this, but I just like to have, since this third row starts with the 1 in the third column, I like to put that in since the first row starts with the 1 in the third column and has zeros to the left of that, I like to put it at the bottom. So I'm just interchanging these rows so that that one will be at the bottom. So that was row 3. Row 2 is unchanged. And now in row 3 is what used to be row 1. Now I'm going to take and I'm going to add negative 2 times row 2 to row 1. And the reason I'm doing this is I want to clean up this, I want to clear up as much as I can from this second row, or from the first row. So adding that is going to give me, well, 2 plus a negative 2 times 1 is 0. 2 plus a negative 2 times 1 is 0. Negative 1 plus a negative 2 times 1 is 1. And 2 times 0 plus 0 is 0. And the second row stays the same. And the third row stays the same. Now, just to make, for reasons that won't be clear for a while, I'm going to interchange row 1 and 2. The reason for this is I'm not going to cover in this video. For this, you don't need to do it, but it will make it look nicer because I don't like starting with zeros. So I get 1, 1, negative 1, 0, 1, 1, 0, 0, 1, 0, and the third row is unchanged, 0, 0, 1, negative 2. Then I'm going to add row 2 to row 1. And what that gives me is 1, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1, negative 2. Now things look pretty good, but let's go ahead and this one sitting right here. I want to take that one and I'd prefer not to have that be a 1, so I'm going to add negative row 2 to row 3. When I do that, I get 1, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 1 plus a negative 1 is 0, and negative 2 plus a 0 is negative 2. And so if I were to read this, what I would get is x1 plus x2 is equal to 0. That's fine. The second row gives me x3 is equal to 0. Okay, now I know what x3 is. And the third row gives me 0 is equal to negative 2. And that's the problem. I can't make that be true no matter what I do. So there are no solutions that make that third row be true. But this is an equivalent matrix, so the set of equations that I got are equivalent to where I started. So there are no solutions to where I started. Finally, let's look at one last version. Let's look at the version x3 is equal to 0, x1 plus x2 minus x3 is equal to 0, 2x1 plus 2x2 minus x3 is equal to 0. This was the system that when we did it, we found that there were infinitely many solutions. And so when we look at this one, we're going to write it as a matrix as 0, 0, 1, 0, 1, 1, negative 1, 0, 2, 2, negative 1, 0. And so what I'm going to start with is I'm going to interchange row 1 and row 3. Once again, I don't have to do this. I just think it looks nicer if I do. So I get 2, 2, negative 1, 0, 1, 1, negative 1, 0, and 0, 0, 1, 0. Now I'm going to add row 3 to row 1. That's going to give me 2, 2, 0, 0, 1, 1, negative 1, 0, 0, 0, 1, 0. Now we add row 3 to row 2. When I do that, I get 2, 2, 0, 0, 1, 1, 0, 0, and 0, 0, 1, 1. Now let's add 1/2 row 1. Actually, I'm going to do an extra step first. Let's scale row 1 by 1/2. So I'm multiplying by row 1 by 1/2. That gives me 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1. Now we add negative 1 times row 1 to row 2, which gives me 1, 1, 0, 0. That doesn't change. 1 plus a negative 1 gives me 0. 1 plus a negative 1 gives me 0. 0, 0, and 0, 0, 1, 1. Just because I don't like that row of zeros in the middle, I don't think it looks nice, I'm going to interchange row 2 and row 3, which gives me 1, 1, 0, 0, 0, 0, 1, 1, and 0, 0, 0, 0. So this system of equations now looks like x1 plus x2 is equal to 0. That's the first row. The second row gives me x3 is equal to 1. And that doesn't, because I made a mistake. And this happens a lot. You have to be careful with this. But if you look from here to here, I changed this 0 into a 1. So that should be a 0 instead of a 1. And that I have to correct that change all the way up. So it gives me x3 is equal to 0. x1 plus x2 is equal to 0. x3 is equal to 0. And the last row just tells me that 0 is equal to 0. Well, that doesn't tell me anything. It's true, but it doesn't change anything. So what I know is that solving this equation, I can say x1 is equal to negative x2, and x3 is equal to 0. So I can't tell you exactly I can't tell you exactly what the x1 is because no matter what x2 is, I can find an x1 that works. And so if I look at the graph of this, in the graph, this line is being represented by some number t as x1, and the negative of that number t is x2, and then x3 is 0. And so that line is built from this set of solutions. So I could write this as x1 is just negative x2, x2 is x2, x3 is 0. Or if I don't want to use the letter x2 or the name x2, I could write this as negative t, t, 0. Or instead of t, I could use negative t and write this as t, negative t, 0, which is what I did on the when I graphed it. So that is everything I wanted to talk about for this video. In the next video, we will talk about more about why I like to do things like have the bottom row be the all 0 rows if I've got it, instead of and get it into this form. So next class we're going to talk more about this form and how we get it into that form, and why that form is a good form and a nice form to work for. So with that, I thank you for listening, and I will see you next time.